Um, Today, my lecture, I'm focusing on centrifugal pumps. Centrifugal pumps are used to move the fluids, and so the fans, so also the fans, and fans move the air, and whereas centrifugal pumps move the fluid. That's the difference. The objective, overall objective of this fluid movement is to comprehend basic operation and characteristics of the pump, um, and also know the Bernoulli's principle, the concept of pressure, net positive suction head, head delivered, pump efficiency, and losses. So those are the objectives. The background is fluid are to be moved through flow systems using pumps, fans, blowers, and compressors. It is a basic mechanism we need to move from fluid from point to point. For example, if you have a internal combustion engine, the gas tank has a gas, and you're pumping gas from there to the engine. That is, you're moving the fluid. So that's where you use the pump. So the fans and blowers and everything, there are different mechanisms. These are all different mechanisms to move different things, but generally you are moving the fluid. Such devices increase the mechanical energy of the fluid. The additional energy can be used to increase velocity, pressure, and elevation. So basically, in a stationary fluid, you are drawing the fluid into the pump and imparting some energy to build the momentum. And that momentum is what's going to convert into velocity, pressure. And if it is elevation, if you have to pump certain feet high above the ground, and that is the elevation. That means you have to have the pressure to move the fluid. And pump, fan, blower, and compressor are terms that do not have precise meaning. So they are interchangeable depending upon how you use it. Generally, pumps move liquids, while fans, blowers, and compressors add energy to gases. So if you're having a refrigerator in your system, you will be Freon would be in a gas mode, and you're going through the compressor to push the hot gases into the um, into the heat exchanger that converts into liquid, and these are the mechanisms. But generally, again, you're moving fluid, that's the gas, from one point, whereas pumps, you're moving liquids. Pumps and fans do not appreciably affect the density of the fluid that they move, and thus incompressible flow theory is applicable. That means you are not compressing them, you're not increasing the density. We're talking about pumps now. So pumps are not changing the density of the media you're trying to move. Here, in our case, here, liquids. And the different between pumps and fans, compressors. Here, pumps, when you put it in simplified terms, you say pumps move liquids, fans move gases with a little increase in pressure, and also compressors move gases with a greater increase in pressure. So that's why you need to have a very high pressure system for the refrigeration, so you are using a compressor. So and um, other, it will be going deeper into this pumps, fans, and compressors. Turbo machines change energy level of flowing fluid by means of momentum exchange. I think I told you about it. So um, the this pumps, the usage and importance of pumps is second only to electric motors in numbers, because for every application we have some motors. Even your PC and your laptops and everything has a motor, and even to run the pump you need a motor too. So, but pumps are, also pretty widely used, and these are the is a list of the usage as given on the screen as you see it. And I'm going to skip the valves. Valves has its own importance, but since I'm focusing on pumps, I want to stay to that subject. So I'm going to move a lot of slides here. Just be patient with me. And we'll cover those in one of the separate class, but right now our focus is um, fans and pumps. The fans way to define is some principle a non-positive displacement pump, like a centrifugal, majority used for compressors, and the axial is cooling fans. You use it in your home. And there his kind of the schematic shows radially the flow is coming in the inlet of the fan and is uh, pushed out on the circumference of the fan blade. And so you have axial flow. That's what axial flow is. And the centrifugal um, type is there are two different types: a propeller type, two stage. That means there are two propellers one after another. You're taking one propeller is drawing air, and then it is being pushed to the second propeller that is increasing the momentum further and moving it. So it's just like a depend upon the we're trying to increase the volume of the fluid um, or the pressure of the fluid. It is used in that sense. In the next few slides, I'll cover a little bit more into it. Now let's focus on pumps. That's the main topic for ours, and I think let's stay focused in this one now. Definition: what is pump? Device that uses an external power source to apply force to fluid in order to move it from one place to another. So you have a stationary fluid, you're sitting in a gas tank or fluid tank or whatever the tank is. You have to um, draw the fluid into the pump. That means something has to rotate to move it to create a suction, and from the suction, the energy of motor as it's rotating, it creates a centrifugal force on the fluid, and that converts into the momentum, and that momentum increases the pressure, and that pressure helps to push the fluid either above or sideways or however you want it. But I think so. It is to make the pump function, you have to have an attachment of the motor. So without that, pump is not going to move much by itself. So that means you need some mechanism. The mechanism is connecting with the motor. So what is but once you have established a motor hooked up to the impeller, so what's to happen? Frictional forces from large quantities of the fluid. That means as it is moving through the pipes and valves, you will have some friction. So that means you are overcoming the friction in the pipes and also in the valves. And then the other one is difference in static pressure between locations. So whenever you make a turn, you have to have more. You have to have a force for the fluid to turn. So these are the things pump has to do to move the fluid from one point A to point B. Must provide a velocity desired. That means if um, you have to have so much quantity of fluid, that means you also have to have so much pressure to overcome. So that means velocity comes into picture. To maintain, the pump has to run at certain speed to get the velocity so that it can build the pressure and push the fluid forward. Types of pumps. Generally, there are two types of pumps we have. One is a positive displacement. The other one is a dynamic pump. Positive displacement pump uses plunger, piston, rotary. I think I'll show you some of them. So positive displacements are basically have a very low flow rate compared to the dynamic pumps, and also but they develop a very high pressure. Give an example. Let's take the automotives. For if you have a fuel, for example, fuel injector, right? So to create a very fine atomized particles to create a spray inside the engine cylinder, that means you need a very high pressure. We're talking about megapascals. So that's where the positive displacement technology shines. So they are low pressure, low flow rate, but high pressure. And And also because the nature of the design, they are pulsating. It's not not smooth flow. That means from time to time you see a small fluctuations of pressure. And whereas dynamic pumps, like our centrifugal pump, that's where we'll be doing most of our lab work, is a very high flow rate and a low uh, pressure. It won't develop the megapascals what I talked about, maybe kilopascals type of arrangement, I mean, capacity. And also, but it is a steady flow. It will have it won't have a lot of pulsations in the pressure, but whatever the pressure is developed, it is pretty steady, constant pressure. So centrifugal pump, where do we use this? Very big, whenever you have a high volume displacement. For example, the golf courses, very large quantity of fluid is being moved. So that's where you use. And also even at homes, when you have a small house and still it has to pick up the fluid from the well and push it up, and that's where you need a centrifugal pump also. So it's a wide variety. It has a low volume to the high volume. It can do it, and it's cheap. The technology is relatively inexpensive compared to positive displacement. But in otherwise, positive displacement, the technology is so precise and the construction is so precise, high tolerances, I mean very tight tolerances, that makes the product expensive. So that is another difference you can add on, is positive displacements are higher cost versus compared to centrifugal pumps. So you get an idea about types of pumps. Components of pump: drive mechanism, steam, electric gear. So as I mentioned, the impeller won't rotate by itself. It has to have a mechanism to drive it. So use an electric motor, or you can use the gears. In the past, they used to use steam engines. Maybe in some areas still they have a use for it. And then that means it has to be connected uh, through a shaft to this driving mechanism. An impeller or piston, these are the um, elements that move the fluid, that creates a suction and that draws the fluid into the pump. And then as it's running at a certain RPM or speed, it develops enough momentum to push the fluid further. And then it has to be all enclosed in a casing. So you would have to have a casing attached to it. This is very important, pump efficiency. How do you calculate pump efficiency? So we know basic formula, efficiency is nothing but output or input. But in our case, when applied to the centrifugal pump, the output is the water horsepower. That means the water that's coming into the pump section, and that whatever the power is required to bring the water. And the brake horsepower is what the motor is, it has to run, right? It has to have electrical power, and thus brake horsepower is the electrical power used to drive the motor. So that the ratio of that is pump efficiency. So one way to calculate work horsepower, I mean water horsepower, is head. Again, the head is we use the head and pressure interchangeably. Whatever the pressure is developing, and the flow, the quantity. I mean, I'm talking volumetric flow, and specific gravity divided by 396. These are for the English calculations. And also when you talk about brake horsepower, again head, flow, specific gravity, 39, and the efficiency. So whatever what the pump efficiency is, ratio of this, if you know the efficiency, if you know the water horsepower, you can calculate the brake horsepower. So that is the relationship. But what is important for you to know is pump efficiency is output or input, that is water horsepower over brake horsepower. When I cover the lab showing our equipment where you're going to be using for this one, I'll show you, how, where are these what is water horsepower, what is brake horsepower, so that at least you have a kind of connection to the equipment we're using it. And talked about types of pumps. Let's go a little bit deeper into positive displacement. So positive displacement is fixed volume of fluid is displaced during each cycle regardless of static head or pressure in pumping air. So every time one revolution is taking place, some amount of fixed volume of fluid is displaced. So for each revolution, you have certain volume displayed. But it is irrespective of downstream pressure, because remember, you're pushing the fluid against some head, some resistance. So, and also positive displacements are known to build very high pressures. So I'll explain to you the mechanism, how they are different than centrifugal pumps, and why they develop high pressures. So again, typical mechanisms for the positive displacement is a piston type pump, and a gear pipe pump, a screw pump. These are all examples of positive displacement. And here is the pictures of the positive displacement. One thing I want you to know: positive displacement are expensive because you need a lot of precision. So the gaps between the rotating mechanism and the stationary mechanism is very tight, and the whole idea of making them precise and tight with a low clearances is you don't want, once the pressure is developed, it try to leak. So you're, by having a very tight tolerances, you're preventing that leak. When I'm saying leak not outside of the pump, within the pump itself. Within the pump itself, you wanted to have minimized leak. For example, if you take this mechanism, there is a element, is an inner rotor, there's another outer rotor, and as the fluid is coming in, there's one, maybe this may be the inlet and this may be the outlet. That means fluid is coming in and fluid is going out. And here is another one, inlet, outlet. So the casing, and between the casing and the inner gear, the two gears are there. The gap between those gears is so tight, there's just barely space to move around. And then as the fluid is coming in, that's where in that gap the fluid is wedged in between, and then as the rotation motion imparting centrifugal force to it, and that centrifugal force builds the momentum, as that momentum converts into pressure. So there's no very minimized leak inside, and that's what is causing the high pressure system. So same thing here, another mechanism, two gears, and they're meshed together, and very tight clearance on both sides. And as the fluid is coming in between those two gears, whatever the fluid is picked up, it is squeezed and then moving out, and that is the discharge is where the high pressure is coming out. And there is another example of screw type pump. Here is another mechanism where the fluid is coming in, going to the screw, and the fluid is moving between the screws. And I think maybe this may be a good example here. You can see how the fluid is squeezed between the casing and the gear tooth, and then when it exits, it comes out with a very high pressure system. Maybe this is the best example. Visually, you can see why, how they develop high pressure system as opposed to the centrifugal pumps. When I show you the centrifugal, it makes sense, why this pump is able to, has a capability. So positive displacement pumps are used when higher head, that means higher pressure increase, are required. Generally, they do not increase velocity. So the pump, that means you don't have a lot of volume of fluid, but you have less volume but high pressure. That's a usage. Positive displacement, some more examples are there. You can take a look at it. But here is another screw type pump, which we talked about it. Very tight tolerances between closed things. And so now dynamic. The word is positive and non-positive. So dynamic pump falls under non-positive displacement. Volume of fluid is dependent on static head pressure. So it can develop on certain pressure. It don't have capacity, and but it is good at developing a high volume of fluid displacement. So centrifugal pump, the way to understand is the impeller inside a casing. Think about it. You have a casing and the impeller is sitting inside. That casing is called volute. An impeller is a disc curved vein show up. I'll show you what it is. Basically, a disc where the veins are put in place, welded or machined or whatever you can call it. They're radially, just like a paddle wheel, and suction is the eye. So it is the center of the pump where the fluid is coming and it's exiting from the 90 degrees radially. It is exiting, and the propeller uses prop inside the casing to move. So he's showing you centrifugal functions, and basically he's using. So let's go to let me show you the picture. Okay, this is a good example of how the system is. So what you're this is a cross-sectional view, and here is the center of the shaft is driven by a motor, and this is where the fluid motion is taking place. So the fluid is coming in and distributed, going into the veins, and those veins are throwing the fluid radially, both sides. And here is the volute is the casing, and for example, this whole shape what you have that is called volute, and here is a pump rotating and is throwing the fluid particles, in a radial direction, and that motion, the centrifugal force exerted on the fluid particle is creating a momentum. So it will develop certain pressure, but not like positive displacement, and that pressure is used to push the fluid against some head. So then again, where is the fluid is coming from the center. So the fluid is coming in the center at 90 degrees to this volute is the outlet. So this is the inlet and this is the outlet, and this is the disc with a lot of veins, and so maybe this also gives an example how the fluid is coming in and how it's dispersed. So he's showing both ways. Maybe okay. Most common type of pumping machinery. So there are many types and sizes and designs, forms, various manufacturers who also publish operating characteristics of each pump in the pump. So one of our main objective in this lab or in this centrifugal is what are the characteristics of each pump? How do the flow changes? How does the pressure changes? And how, when you have a resistance downstream, how the pump behaves. So these are the things we'll be checking it out, and our testing and collecting the data to understand how is the pump performance is, how is the efficiency is, and also how is how good it is against the resistance of the downstream valves and also the friction of the pipes and things like that. Pump curve describes delivered pump efficiency and net positive suction head for a property operating specific models. Centrifugal pumps are generally used where high flow rates and moderate head increase are required. I think we talked about it. I think golf course is a good example where you need a high flow, not a lot of pressure. So that's where you use. Now this gives a little bit more understanding of it. Think about these are all fluid particles coming into a disc, and the disc is both sides are enclosed, but these veins, what you see where the fluid is coming out, they're curved shaped veins. They're not straight veins. It's not going diagonally, out into the outside radius. They are curved shape, and that causes enough momentum on the fluid particles that is required. And also when you have the curved shape, it generally increases the efficiency. So liquid is directed into the center of the rotating pump. This is where the center is rotating. Impeller is picked up by impeller's veins, and then it picked up by these are the veins you're seeing, 1, 2, 3. These are the veins. They're curved shape. Picked up by the impeller veins, accelerated to higher velocity. So that as it's rotating, the particle is the energy is imparted to the particle. As the energy is imparted, the velocity of the particle increases by the rotation of the impeller and discharged by the centrifugal force into the diffuser. Diffuser is what I talked about, the volute. The volute is where it is collected later, and then it is exits through outlet plate. Centrifugal pump chamber, a collection chamber in the casing converts much kinetic energy due to velocity into pressure head. So that is where because you need a certain pressure also. So if you don't have pressure, you cannot push the fluid further. Or if you want to push the fluid into 100 feet tall, tall building, you need some pressure has to build up, and that the casing is acting like a device to convert the kinetic energy into a pressure head. Another, he's showing you what it is, diameter, impeller thickness. So he's giving you these important characteristics for a reason. The reason why he's showing is, hey, whenever you have a design a pump, you have an impeller, it has a certain diameter, and if you increase the impeller, the volume of the fluid increases. If you increase the thickness, you also increase the volume also. So he's trying to show thickness impeller, more water, thicker the impeller, larger the diameter, more pressure. Now see the relationship. If you want to increase the volume, make it thicker, and if you wanted to increase the pressure within the parameters, you need a bigger diameter. So you have 10 inches versus 100 inches makes a big difference. And increase in speed is another one. More speed, you have a more pressure is also developed. More water. That means with the first of all, the three variables you identified. One is thickness of the impeller. That more higher, thicker it is, more water, and diameter. Higher the diameter, more pressure, and speed. Higher the speed, more it increases both of them, volume of the fluid and also the pressure. But you have within the ranges. It all depends on how much motor can generate. So the other way things we can also do is put two impellers side by side. So when you do that, you're not going to increase much of the flow, maybe a light, but you are definitely increasing the pressure. So twice the pressure, same amount of water. So volume won't change, but increasing the pressure. For example, I need a 200 kPa, but my impeller develops only 100 kPa. So that means I can put two impellers together and get my 200 kPa. Multiple series. You can also, if you wanted to have a higher pressure, you can line up 2, 3, 4 impellers, provided you have the room for the casings and things like that. So then we're going to switch our subjects into the flow meter. Okay, now we know how to move the fluid from point A to point B, but at the same time we need to measure them. The measuring is what called flow meters. The word is rotometer is used, and this is the one is on the picture is a very old design, but works perfectly fine, cheap, but it has its use. It has to be in vertical. You cannot be making it in horizontal. So I think when you really go into precise measurements, this is not the equipment you use. You have the turbine measurements. So anyway, you use measuring flow rates, volumetric flow rates, uses the equations to convert mass flow rate when it needed. So that means if you are measuring in volume by multiplying with the density, you convert into mass flow rate. So other technology, right now we talked about one technology. The technology is a rotometer. This is a very simplest technology. All it is a tube, is a tapered tube, and there is some bobbin inside our metering float, and the fluid is coming in, and as the flow increases, this bobbin lifts up more because against the gravity, higher the speed, and that the way it is calibrated is given the fluid density, the scale is developed. So the other one is turbine flow meter, where the fluid is going and the turbine is rotating, and that converts into electrical signal an electrical signal is converted into the volume of flow that is going through. So there is another one, paddle wheel design. A lot of flow meters are there, and so just since we are working on the centrifugal pumps, I want you to get to know the terminology. It's very important understand the terminology. What is vane? What is eye of the impeller? What is inlet? What is outlet? What is volute? What is impeller? What is flange? One should know the basic things. Okay. Another thing is pressure, head. Head in terms of expressing feet of water or meter of water of a column. So that's how you say it. So head and pressure, they are all interchangeable. Head can easily convert into pressure. So you multiply with the conversion. So if you have a 100 feet tall reservoir and if it's showing a 43.3, that will show 43 points. So the relationship is 100 feet of water is equal to 43.3 psi. So you use that conversion factor so to measure the relationship between head and pressure. Head and pressure are interchangeable, as I mentioned, provided that they are expressed in the correct units. So always the units are anything you do fluid labs and things like that, you have to be very precise on your units. As an engineer, one should know what are we doing. What is the flow? Is it a gallons per hour or gallons per minute? And so you need to have a very clear distinction about the units. And the conversion of all pressure terms into the unit sequence simplifies most pump calculation. Then why we use head? Why we're not using pressure? Because to simplify our calculations is much easier to deal with it. And also in the past, we used to measure things in terms of elevation, and head is pretty good measure to understand. If you say 43 psi, we don't know, but 100 feet of water is easy to imagine. So that's it. So another important characteristics is this slide here. What it's showing is volumetric flow rate, that is gallons per minute, okay, or liters per minute in other unit. So like metric versus is in relation. The relationship is proportional to the speed of the pump. So these three relationships I really want you to remember, very important. The other one is horsepower head discharge pressure, whatever the pressure division psi is G you're measuring, is proportional to the speed of the velocity. I mean the speed square. And power required, that means to run the pump motor, is proportional to speed cube. So these are the basic relationship. I want you to remember those. And the second one is when it comes to pump, the biggest thing is cavitation. What is cavitation? Cavitation is a formation of bubbles, and it happens in certain conditions. And that bubbles cause a lot of damage to the pump impeller, and at the same time, in a gas pumps, especially when I say gas, the pump that used in automobiles, they create a vapor lock. That means fluid cannot go any further. It just locks up the entire flow of the pump. So that's why we have to be very careful how your suction pressure is. So, so what is cavitation? The formation of bubbles due to low pressure area and the subsequent collapse upon the migration. So if the inlet of the pump having a very low pressure, negative pressures, because the motor is it is running at a certain speed, and it's creating a pressure which is below the vapor pressure of the water, if it is pumping water, or below the vapor pressure of the gas, or whatever the fluid they are running. If it does that, it creates cavitation. So that cavitation is very harmful. And what does cavitation do? Causes noise and also damage. You see the erosion taking place on this impeller. So net positive suction head, what is that? Need enough pressure on the suction side. We're talking about suction, not on the downstream of the pump. Suction side, that pump does not reduce pressure at the eye to cause pressure is less than P saturated. Saturated means the saturated pressure of the liquid it is pumping. It has to be less. If it is I'm just giving an example, 100 kPa is the saturated pressure of the whatever the liquid you are using. It has to be the pressure that is the suction of the pump has to be, more. That's the only way it stops cavitation. So it says P should be equal less than P saturated water flashes into vapor, causing damage to the pump. What are positive means of providing NPS to prevent cavitation? So he's showing you some. So what he's saying in net positive suction head is pumps cannot pump vapors. If you do that, I told you again example vapor lock, and the satisfactory operation of the pump requires the evaporation of the liquid being pumped does not occur at any condition of the operation. So I think not related to subject. I'll tell you, especially with the gas pump, when you go to the higher value aviation, the water gas evaporates much faster. That means the suction pump is another issue. So your pump should be able to handle in those conditions. That means you should design in such a way that the vapor pressure won't drop down to that of the saturation pressure of the liquid. He's just giving some example, something to read and remember. And let's talk about pump performance. And we're going to stop at this point after this slide. I'll explain to you everything. So typically, this pump performance, one has to be literally memorized. The reason is this is how the pump behaves. What we have here is on the x-axis you have flow, capacity in US gallons per minute. That is a flow basically, right? Gallons per minute or gallons per second, whatever the flow is. And then he's giving you the head, that means the pressure the pump develops. So looking at this, immediately what comes to your mind is at zero flow, that means you're not there's a pump is running, but it is a zero flow, nothing is generated. That's where you have the highest pressure you can develop. Now, as you increase the flow, the pressure drops. So, for example, if I am running at a full capacity, 60 gallons per minute, so, but if you look at my pressure, it's almost zero head. That means I have a lot of flow, but I don't have a head to push the fluid forward. See that, the relationship? So that when you read the graph, what you should know, if I have a zero head, my flow would be the max. And if I have a zero flow, my head will be the max. See the relationship? So this is how pump, generally centrifugal pumps, this is how they behave. So this is a basic fundamental thing one has to understand is how this is what called performance of the pump. So when you collect the data, you'll see how the performance. So when you have a very low pressures, the head is high. For example, I have 10 gallons per minute, right? My pressure is almost like I would say 35 more plus 37, 38 feet of water I can pump. But if I have 50 gallons per minute, I can push only up to less than 20 feet of water. Did you notice that? So that's how the relationship is there. So as the flow increases, head goes down. As flow decreases, head goes up. That's the relationship I want you to remember. So with that one, we'll stop. And I think probably what we'll do is we'll do another lab where I'll show you the pump, how the operation is. And then in that one, I'll mention you what are we doing in the lab, what kind of data we are collecting. And there are 3-4 graphs we'll be doing in this lab. I'll go over those graphs in a detailed way so that it makes sense to you. But right now, I'm trying to give the theory of the centrifugal pump and how the pumping operation is, what are the characteristics, how to calculate the efficiency, the types of pump, just trying to do. But obviously, I'm not covering the valves here, and I think that's not part of my discussion on this subject. And with this one, and I'll close it. And next class, we'll focus on, we'll do it right by the lab itself, and I'll show you the graphs, what we'll be doing it. And I think probably that would be the thing.